Can you imagine our solar system 100 million years from now? The layout of Earth's continents will be completely transformed, and the sky and seas might look like they belong to an entirely different planet. The span of 100 million years is an unimaginably vast timescale compared to human history. Considering that our civilization only began a few thousand years ago, the world, 100 million years from now, will be filled with surprises beyond our wildest dreams. The Earth's landscapes, its climate, and even life itself will have undergone dramatic changes. But what about the Sun and the other planets? We'll take you on a journey through time. Let's explore the astonishing future of our solar system 100 million years from now. Together, the transformation of Earth. First, let's start with Earth. What will our blue planet look like in 100 million years? The world map we are so familiar with today will likely be completely redrawn by continental drift and plate tectonics. Plate tectonics is the mechanism by which the rocky plates on Earth's surface move over long periods, causing continents to break apart and come together. This movement has led to the formation and breakup of several supercontinents in the past, such as Pangaea. So, what does the future hold? According to scientists' simulations, about 100 million years from now, the continents will reach their maximum dispersal. After that, they are expected to begin colliding and merging once again. In other words, after our current continents spread even farther apart, they will start moving toward the formation of the next supercontinent. Further into the future, about 200 to 250 million years from now, the currently separated continents are expected to reunite into a single landmass, creating a new supercontinent. There are several hypotheses about what this future supercontinent will look like. For example, one scenario, known as Amarcia, suggests that the North American and Eurasian continents will collide and merge in the Northern Hemisphere. Another scenario, called Pangaea Ultima, or the next Pangaea, proposes that the Atlantic Ocean will close, joining Africa and the Americas. In any case, on Earth, 100 million years from now, the continents will be gathering in a configuration completely different from today, and our world map will have undergone a radical transformation. So, what will Earth's environment be like then? Changes in continental arrangement have a massive impact on the climate. For instance, when multiple continents collide to form a supercontinent, the emergence of high mountain ranges can alter atmospheric and oceanic circulation patterns, making the interior of the landmass more prone to dryness. Furthermore, the birth of a supercontinent could dramatically change the global environment. The mountain-building activity caused by plate collisions, known as orogeny, could change wind and rain patterns, and some speculate it could even lead to a cold ice age. If all the land gathers into one place, the distribution of ocean currents will also change. Ice sheets might develop along the coastlines, potentially causing sea levels to fall. On the other hand, when continents merge, the process of weathering, where rocks on the crust are eroded by wind and rain, is accelerated. This could lead to a decrease in atmospheric carbon dioxide, weakening the greenhouse effect and causing a drop in global temperatures. Interestingly, this is also predicted to result in an increase in atmospheric oxygen levels. Looking back at geological history, for example, during the late Paleozoic era, from about 570 million to 250 million years ago, when the supercontinent Pangaea existed, Oxygen levels were high. Later, in the Triassic period, when Pangaea began to break apart, oxygen levels dropped. It's possible that a future supercontinent could similarly see a rise in oxygen due to changes in ecosystems and the carbon cycle associated with the concentration of land masses. However, Earth's history is also a cycle of cooling and warming over a period of 100 million years. We might experience several ice ages, where the entire globe is covered in ice. Alternating with warmer periods, we are currently in an interglacial period, a warm spell between ice ages. But the warming caused by human use of fossil fuels is temporary, a brief moment from the perspective of global climate cycles. In the long term, factors like plate configuration, changes in Earth's orbit, and the increasing brightness of the sun will continue to bring about both ice ages and periods of intense greenhouse effects. So, what will the specific climate of Earth be like in 100 million years? Current simulations suggest that in about 50 million years, the continent of Antarctica will move northward, away from the polar region, and its massive ice sheet will completely melt. At the same time, if Greenland's ice sheet also melts, sea levels are expected to rise by as much as 90 meters compared to today. 100 million years from now, the coastal cities we know today will have long vanished beneath the waves due to this kind of warming-induced sea level rise. From the tropics to the temperate zones, the sea may have intruded deep into the continents, creating shallow inland seas that don't exist on our current maps. For example, if the Australian and Asian continents collide, the former Indian Ocean could be trapped between them, potentially forming a gigantic inland sea. Also, if Europe and Africa collide and the Mediterranean Sea disappears, a vast new generation of mountain ranges, future versions of the Alps or the Himalayas, could tower there, influencing the climate. Meanwhile, the interior of the supercontinent, being far from the ocean, might receive little rain, leading to the spread of vast deserts. If we were to visit the Earth of that time, we would be astonished by the desolate landscapes of the continental interior. Along the coasts, seasonal monsoon winds would blow, creating entirely new climate zones. Furthermore, with changes in continental layout and temperature, ecosystems will also change drastically. 100 million years from now, the cast of life forms will surely be vastly different from what it is today. Just as new species have emerged after past mass extinctions and environmental shifts, many of today's organisms will have disappeared in the future Earth, replaced by newly evolved life forms that dominate the planet. For example, mammals and birds may have evolved further, and animals with appearances we've never seen before might be roaming the land. Plants, too. They will likely have taken on forms different from the flowers and trees of today. And what about humanity? 100 million years is more than 300 times the approximately 300,000 years that Homo sapiens have existed. In fact, our human ancestors only appeared a few million years ago at most. So the probability of modern humans existing as we are in 100 million years is extremely low. As we'll discuss in more detail later, whether humans and other large animals can survive depends on countless challenges, such as changes in the natural environment and celestial impacts. In summary, the Earth of 100 million years from now will be a completely different world in terms of its geography, climate, and biosphere. The continents we know will have merged into a supercontinent, and the climate will fluctuate dynamically under its influence. Sea levels may be higher or lower than today, depending on the era, but in any case, the face of our planet will be magnificently transformed. It's exciting to imagine how humanity, par its descendants, will have adapted to such an Earth. Next, let's turn our gaze to the Sun, which continues to illuminate our planet. The future of the Sun in 100 million years. The Sun will be slightly older than it is now. However, from a human perspective, the difference is unimaginable. The Sun is currently about 4.6 billion years old, and in 100 million years, it will be about 4.7 billion years old. It will still be in the latter part of its middle age, just past the halfway point of its roughly 10 billion year lifespan. However, this middle age change in the Sun is already beginning to slowly affect the entire solar system, including Earth. The Sun shines through nuclear fusion, and its brightness is gradually increasing over time. In fact, the Sun's luminosity has been increasing almost linearly from about 70% of its current brightness at its birth. This rate of increase is estimated to be about 1% every 110 million years. This means that 100 million years from now, the Sun will be about 1% brighter. It may seem like a small change, but it's enough to affect Earth's climate. A 1% increase in brightness means that the solar energy Earth receives will also increase by about 1%, which could raise the average temperature by several degrees. Why is the Sun getting brighter? Inside the Sun, a nuclear fusion reaction is converting hydrogen into helium. As the hydrogen in the core gradually depletes, the core will contract, and its temperature will rise to maintain the efficiency of fusion. As the core temperature increases, the remaining hydrogen burns faster, causing the Sun's total energy output to increase. Through this process, the Sun gradually becomes brighter and larger as it ages. 100 million years from now, the Sun will be slightly bigger and shining hotter than it is today. The Sun in our sky will still appear yellow, but its light will be more intense. And the ultraviolet radiation pouring down on Earth may also have increased. The rise in the Sun's luminosity will have a direct impact on Earth's environment. As mentioned in the section on Earth, the brightening of the Sun will advance global warming, making ice sheets and glaciers more susceptible to melting. On a timescale of tens of millions to 100 million years, the warming effect from the Sun's increased luminosity is expected to melt the ice in Greenland and Antarctica, leading to a rise in sea levels. Conversely, there are long-term cooling factors, such as changes in continental arrangement. But given the undeniable trend of increased heat from the Sun, it's highly likely that on a global scale, the climate will become warmer over the next 100 million years. Polar regions will be warmer than they are today, and an era may come when forests flourish even at the South Pole. If high-latitude regions warm up, the habitable zone for humans could expand to the Arctic and Antarctic circles. Ultraviolet and other radiation from the Sun will also increase slightly. This increased UV radiation could affect the ozone layer in Earth's atmosphere. Fortunately, on a timescale of about 100 million years, a catastrophic collapse of the ozone layer is not expected. However, over the course of many more, hundreds of millions of years, the Sun will become so bright that it will trigger a runaway greenhouse effect. For instance, in about 1 billion years, the Sun's luminosity is estimated to be more than 10% higher than it is today, which will plunge Earth into a hothouse state where its oceans boil away 100 million years from now, is still before that point. But the signs of environmental change caused by the increasing heat from the sun will surely be apparent. Another point of interest is the solar wind, the stream of high-energy particles flowing out from the sun. Generally, stars emit strong, stellar winds when they are young, and as their rotation speed slows down, the winds weaken. The sun is already in its middle age, and its rotation is slower than in its youth. So extreme, violent solar winds are less frequent. However, over a 100 million year period, the nature of the solar wind could change, along with the sun's brightness and activity levels. Solar activity, such as the number of sunspots and the frequency of flares, is thought to fluctuate slowly over the long term. So it's not a given that the solar activity cycle 100 million years from now will be the same as it is today. Perhaps solar flares, surface explosions on the sun, will be calmer than they are now. Or conversely, their cycle might be longer. However, the intensity of the solar wind itself is not expected to change dramatically. Earth will continue to be protected from the solar wind by its magnetic field, which prevents atmospheric stripping. On the other hand, for a planet with a weak magnetic field like Mars, atmospheric stripping by the solar wind will continue slowly. So in 100 million years, its atmosphere will likely be even thinner than it is today. Mars already has an extremely thin atmosphere, and the solar wind is still blowing what's left of it into space. Over 100 million years, the remaining water vapor and gases in the Martian atmosphere will be further eroded, making it an even drier and more barren world. The Sun itself will remain a stable main sequence star, a star in its normal shining phase. A star like our Sun has a lifespan of about 10 billion years. While it burns hydrogen, 100 million years is only about 1 to 100th of that time. Therefore, it will still have plenty of hydrogen fuel left and will not have undergone the massive expansion of a red giant. However, the hydrogen in its core is steadily decreasing, and helium ash is accumulating. As a result, the Sun is destined to become brighter at an accelerating pace. You could say it's not aging, but rather shining brighter in its middle age. This trend is unstoppable by humanity. But since the extreme changes are still far in the future, the Sun will continue to be a precious source of light and heat for the Earth of 100 million years from now. Let's also consider the impact on the solar system as a whole. As the Sun becomes 1% brighter, it will have a slight effect even on the distant planets. For example, the increased heat from the Sun might slightly warm regions that were previously frozen. This could be a small boon for Mars and the moons of Jupiter and Saturn, as we'll discuss in detail later. For Mars, the increased energy from the Sun could raise its surface temperature somewhat. However, Mars's atmosphere is so thin that it has almost no greenhouse effect. So simply increasing sunlight won't dramatically improve its environment. Still, moments when ice could melt and water could flow might become more frequent, such as during the daytime on a summer day near the equator. The real beneficiaries of the brighter Sun might be the moons of Jupiter and Saturn. Jupiter's moon, Europa, and Saturn's moon, Enceladus, both covered in ice, are believed to have liquid oceans in their interiors, but their surfaces are covered by thick ice sheets. If the heat reaching them from the Sun increases, the very surface of the ice might warm up slightly and become more active. Of course, The main source of heat for these icy moons is tidal friction from their planets, so the effect of sunlight is limited. Even so, it might lead to changes like ice fractures or water plumes, which currently happen perhaps once every million years, occurring a bit more frequently. Or consider Titan, Saturn's moon with a thick atmosphere and seas of methane. Increased heat from the sun could alter the patterns of its methane seas and evaporation. Titan currently has a nitrogen and methane atmosphere and lakes of liquid methane and ethane. If the sunlight becomes 1% stronger, Titan's surface temperature would rise slightly, possibly invigorating its methane cycle of rain and evaporation. However, it's important to note that the methane in Titan's atmosphere is thought to break down in a few tens of millions to 100 million years. Therefore, the abundance of methane on Titan today is believed to be sustained by continuous replenishment, perhaps from volcanic activity. It's uncertain whether this replenishment will continue for the next 100 million years. If it stops, methane could disappear from Titan's sky, and the chemical composition of its atmosphere would change significantly. If that happens, Titan's surface would dry up, and the methane rivers and lakes we see today would be gone. Thus, the Sun's evolution, though slow, will steadily impact the solar system. The Sun of 100 million years from now will be brighter and hotter, warming the Earth and bringing subtle changes to Mars and the moons. However, the Sun's truly great transformation into a red giant is still billions of years away. In 100 million years, the solar system will still be in a relatively stable and peaceful middle age. It could be called a temporary stability before the dramatic old age to come. Nevertheless, for humanity, even a subtle change in the Sun could become a matter of life and death. Next, let's turn our attention to the fate of the other planets in the solar system and see what each world will be like in 100 million years. The fate of the planets. Mercury, a scorching destiny. Mercury and Venus, the planets closest to the Sun, are expected to remain harsh, scorching hellscapes 100 million years from now. First, Mercury. Its daytime side currently reaches a brutal 430 degrees Celsius. It has almost no atmosphere and is constantly exposed to the Sun's glare. In 100 million years, as the Sun's brilliance increases, Mercury's surface temperature will rise even further, with some spots potentially exceeding 450 degrees Celsius. Mercury's relationship between its rotation and orbit, a 3-to-2 spin-orbit resonance, where it rotates 3 times for every 2 orbits, will remain unchanged, meaning the same regions will continue to be exposed to the Sun's intense heat over a long period. The rocks and metals on Mercury's surface will weather from repeated thermal expansion and contraction, and some will be blown into space by the solar wind. However, since Mercury is a geologically dead world with almost no activity, its crater-riddled, desolate appearance in 100 million years might not be that different from today. Still, occasional impacts from other celestial bodies will create new craters and topographical changes. For example, on a timescale of tens of millions of years, an impact from a meteorite tens of kilometers in diameter could carve a new, massive crater on its surface. Mercury's orbit itself will remain largely the same. In the very long term, there's a tiny possibility that gravitational interactions with other planets could destabilize Mercury's orbit, but that's a matter for a timescale of billions of years. Over 100 million years, Mercury will continue to orbit the Sun stably. In short, Mercury, in 100 million years, will still be a small ball of rock, continuously baked by the Sun. When the Sun eventually expands into a red giant, Mercury is fated to be the first to be swallowed by the Sun's enormous atmosphere and vanish. But that is about 7 to 7.5 billion years from now. On a 100 million year timescale, Mercury will still exist, simply enduring its harsh environment. Next is Venus, often called the Hell Planet. Venus has a surface temperature of about 465 degrees Celsius due to a powerful greenhouse effect from its thick carbon dioxide atmosphere. The Venus of 100 million years from now will still be a scorching, high-temperature planet. The increased sunlight could make Venus's atmosphere even hotter. Currently, Venus's clouds are covered in a thick fog of sulfuric acid, and rising temperatures might alter the chemical reactions in the atmosphere, changing the composition or density of the clouds. However, Venus's climate system is already in such an extreme state that a 1% increase in sunlight might have little to no effect. In essence, Venus will remain in a state of hyper-greenhouse effect, a world of high temperature and pressure, where even lead would melt on the surface. It's possible that volcanic activity is still occurring on Venus today. Observations from Europe's Venus Express mission have reported topographical changes on the surface that appear to be caused by volcanism. If Venus's magma activity continues, it's possible that several massive eruptions will have occurred over the course of 100 million years. Since Venus is a rocky planet nearly the same size as Earth, it's thought that it might occasionally release its stored internal heat all at once, in events that reset its surface. In fact, one theory suggests that Venus's surface is relatively young, with few craters, because it was resurfaced by global volcanic activity within the last 500 million years. If another such massive eruption event were to occur within the next 100 million years, Venus's surface could be covered in new rock, giving it a youthful topography with few craters. Of course, its environment would remain extreme, with temperatures of several hundred degrees and an atmospheric pressure 90 times that of Earth. A fierceness where not only life, but even human probes cannot survive and operate. Venus, one of the harshest environments in the solar system, will remain a forbidding hell planet 100 million years from now. Like Mercury, Venus is ultimately destined to be swallowed by the Sun's expansion when the Sun enters its red giant phase. Its radius is expected to expand beyond Earth's current orbit of 1 astronomical unit, meaning Mercury and Venus will certainly be engulfed by the Sun. Even Earth has a high chance of being swallowed, but that is a story for the distant future. The Mercury and Venus of 100 million years from now will continue to be bathed in the intense heat and light from the Sun, maintaining their respective scorching infernos. Mars, the possibility of becoming a temporarily habitable planet. Next up is Mars. Mars orbits the Sun at a distance of about 1.5 astronomical units. Outside of Earth's orbit, present-day Mars is a cold, desert world, with an average temperature of around -60 degrees Celsius, an extremely thin atmosphere, and no liquid water on its surface. However, 100 million years from now, a small opportunity might arise for this red planet. As mentioned earlier, due to the Sun's increasing luminosity, the solar system's habitable zone, the region where liquid water can exist, will expand outward. Currently, Earth is on the inner side of the habitable zone, while Mars is near its outer edge. As the Sun gets brighter, this zone will gradually shift farther out, eventually reaching the vicinity of Mars's orbit 100 million years from now. Mars won't be fully inside the habitable zone, but it will be receiving more heat from the Sun than it does today. Calculations suggest that the increase in sunlight will slightly raise the average surface temperature of Mars. Currently, on Mars's equator during a summer day, the temperature can rise to near 0 degrees Celsius in 100 million years. The duration and area where this happens might increase. The ice at the polar caps, both dry ice and water ice, might sublimate a bit more in the summer, being released into the atmosphere as thin fog or clouds. However, Mars's atmosphere will still have a pressure of only about 0.6% of Earth's, and its greenhouse effect will remain weak, even if the sunlight is stronger. The thin atmosphere will allow heat to escape back into space quickly. Therefore, a natural Mars in 100 million years will likely remain a fundamentally dry and cold planet. At night, temperatures will plummet, and the freezing cold of tens of degrees below zero will persist. But if, in the future, humans or some other intelligent beings were to terraform Mars, the situation could change. For example, by releasing massive amounts of greenhouse gases to create a thick atmosphere on Mars, combined with the Sun's increased luminosity, it might be possible to make Mars's environment similar to Earth's. It's not just a dream to imagine a future where we melt the polar ice caps, replenish the atmosphere with carbon dioxide and water vapor, and bring back rivers and seas to Mars. Because Mars is smaller than Earth and has weaker gravity, it would be difficult to maintain an atmosphere for a long time. But on a timescale of about 100 million years, it is theoretically possible for human technology to temporarily create a blue Mars. Research into how we could warm Mars to make it habitable for humans is already being conducted today. Of course, it's difficult with current technology, but with an immense amount of time, like 100 million years, the possibility that humans might have remodeled this planet into a second Earth in the solar system is not zero. Even without human intervention, a scenario where the Martian environment temporarily improves due to natural happenstance is conceivable. For example, if a large asteroid were to collide with Mars, the impact could instantly release ice and carbon dioxide trapped underground, temporarily thickening the atmosphere and causing warming. Some theories suggest that in Mars's past, massive meteorite impacts may have caused temporary periods of heavy rainfall. Over the course of 100 million years, Mars is likely to be hit by celestial bodies several kilometers in diameter. If such an event occurs, Mars might experience a rainy season lasting for several decades, and its dry riverbeds could once again hold water. However, this effect would not be permanent. Even if the atmosphere temporarily thickens, Mars's weak magnetic field and low gravity mean that the solar wind would strip it away again within a few million years. It would likely revert to its original thin atmosphere. By the way, Mars has two small moons. One of them, Phobos, with a diameter of about 22 kilometers, is known to be gradually falling toward Mars. Phobos is approaching Mars at a slow pace of 1.8 meters per century. At this rate, it is expected to either collide with Mars or be torn apart by tidal forces to form a ring in about 50 million years. 100 million years from now, Phobos will no longer exist. It's likely that in 50 million years, A fine ring of dust will hang in the Martian sky, and over the next few tens of millions of years, the particles of that ring will also rain down into the Martian atmosphere and disappear. Therefore, in 100 million years, Mars might have only traces of a time when, unlike today, it temporarily had a ring like Saturn. The lifespan of this ring is estimated to be between 1 million and 100 million years. So right around the 100 million year mark we're focused on, a faint ring might still be present around Mars. Or it might be in the process of disappearing. The other small moon, Deimos, orbits farther out and is actually moving away. So it will still be a moon of Mars in 100 million years. So, the Mars of 100 million years from now will still be a cold and dry planet, but it will be enjoying a bit more of the sun's warmth than it does today. Although the environment will remain harsh, there might be an increase in moments when liquid water can exist near the surface, depending on the location and time of day. If humans or other intelligent beings intervene, the dream of reviving a green land on Mars might have been realized. On the other hand, if left to the course of nature, Mars will continue to circle the Sun as a reddish-brown desert with a thin atmosphere and polar ice caps, but perhaps a faint ring, made from the remnants of Phobos, will be shining in the sky above. A Mars with a beautiful ring, something it doesn't have today. Imagining such a sight is quite romantic, isn't it? Jupiter and Saturn. The impact on the giant gas planets and their moons. The giant gas planets of our solar system, Jupiter and Saturn, will likely maintain their majestic presence 100 million years from now. Jupiter and Saturn themselves are enormous balls of gas, primarily composed of hydrogen and helium. Unlike stars that undergo nuclear fusion, they do not change dramatically on their own. The fate of these planets is relatively stable, and significant changes are unlikely to occur over a period of about 100 million years. However, if we look at the details, there are some interesting possibilities. First, Jupiter. As the largest planet in the solar system, Jupiter will continue to exist without its royal status being challenged. Currently, Jupiter's atmosphere is home to the famous Great Red Spot, a massive storm. However, this Great Red Spot has been observed to be gradually shrinking. It's uncertain whether it will still exist in 100 million years, even if not on the scale of the Great Red Spot. Complex vortices and storms are constantly forming and disappearing in Jupiter's atmosphere. Over the course of 100 million years, a new giant storm may have emerged to replace the Great Red Spot, and the pattern of Jupiter's bands, its belts and zones, will also have fluctuated. However, the overall appearance of Jupiter should still be that of a gas planet, with its characteristic stripes. Looking through a telescope, you would still see distinct brown and white bands, with swirling storms scattered here and there. Jupiter is slowly releasing the gravitational energy it stored during its formation, which causes it to radiate more infrared radiation than it receives from the Sun. In 100 million years, Jupiter's internal cooling will have progressed slightly, and the entire planet might have cooled by a tiny fraction of a degree, perhaps a few millikelvins. That is, a temperature just infinitesimally above absolute zero, minus 273 degrees Celsius. But this is a change imperceptible to human senses. Therefore, Jupiter's physical properties, such as its radius, mass, and rotation period, will be almost the same in 100 million years as they are today. Its orbit is also stable and will not shift significantly. Jupiter is orbited by a multitude of moons, and among them, the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are as interesting as planets themselves. One potential change in Jupiter's moon system over 100 million years is a slight alteration of their orbits due to tidal interactions. For example, Io, Europa, and Ganymede are currently in a 1 to 2 to 4 orbital resonance. This means that for every one orbit Ganymede completes, Europa completes 2, and Io completes 4, creating a relationship like a regular cosmic rhythm. This resonance is strong and will likely not break within 100 million years. But internally, each moon will gradually lose energy through tidal friction. Io is currently volcanically active, but if it continues to erupt for another 100 million years, its interior might gradually cool down. However, due to Jupiter's immense gravity, Io will likely maintain its geological activity for a long time to come. Europa is a moon with an ocean beneath its icy shell, and its surface is covered in ice. Europa's surface is currently very young, and it's thought to be renewed with fresh ice on a cycle of tens of millions to a few 100 million years. In other words, Europa's surface is constantly being rejuvenated as seawater from its interior seeps through cracks and refreezes. 100 million years from now, the surface features of Europa that we see today will be gone without a trace. Covered by new ice patterns, perhaps material erupted from the internal ocean will have spread across the surface. And evidence supporting the current hypothesis that oxygen is being supplied to Europa's ocean might be inscribed in the future geology. Ganymede and Callisto are quiet moons made of a mix of ice and rock, and no major changes are expected. However, Ganymede is the only moon in the solar system with its own magnetic field, and its internal core is slowly cooling in 100 million years. The core will likely still be liquid, and the magnetic field will exist. But in the longer term, the magnetic field is expected to weaken. Now let's look at Saturn. Saturn is famous for its beautiful rings, but these rings are not eternal. Recent research suggests that Saturn's rings may be relatively young, having formed only a few 100 million to 100 million years ago. Furthermore, observations have shown that Saturn's rings are made of tiny ice particles and are raining down onto the planet, pulled by Saturn's gravity. This means that Saturn's rings are fated to disappear over time. Estimates suggest that in about 100 million years, the vibrant rings we see today could become significantly faded. The Saturn of 100 million years from now might no longer have the spectacular rings it has today. If any rings remain, they will be much fainter than they are now. On the other hand, Saturn's moons, such as Titan and Enceladus, will continue to orbit the planet. For Titan, as mentioned earlier, the key question is what will happen to the methane in its atmosphere. If Titan's internal volcanic activity ceases and the supply of methane is cut off, the methane could disappear from its atmosphere, leaving it a dry moon where methane seas once existed. However, 100 million years is not that long for Titan. The large amount of methane on Titan today is likely being continuously replenished by geological activity. So, it's highly probable that some form of methane cycle will be maintained 100 million years from now. In that case, we might see slow changes on Titan's surface, such as the location of its lakes shifting or occasional massive floods. Regarding the origin of Saturn's smaller moons and rings, it's interesting to consider that just as Phobos's fate might give Mars a ring, new rings could form around Saturn from collisions or the disintegration of its moons. Some of Saturn's moons are in unstable orbital resonances, so it's possible that over the next few tens of millions to 100 million years, a small moon could collide and be destroyed, creating a short-lived new ring. However, even if such an event were to occur, most of the debris would quickly fall into Saturn, so the new ring would likely be ephemeral. Jupiter and Saturn, the giants of our solar system, will continue to reign as the gravitational masters 100 million years from now. Jupiter, with its immense gravity, will continue to stir up nearby small bodies, while also serving as a shield, protecting Earth from cosmic threats. Even today, Jupiter attracts or flings away periodic comets and asteroids. Over the course of 100 million years, Jupiter may have swallowed comets that were on a collision course with Earth multiple times. At the same time, Jupiter's gravity can also disturb the asteroid belt and send asteroids toward Earth. The dual nature of this role will be discussed in more detail later, but there is no doubt that Jupiter's presence is crucial for the stability of the solar system. Saturn, too, will maintain its majestic presence, though perhaps with less brilliant rings. As it continues its quiet orbit, around it, Titan might still be shrouded in its pale orange atmosphere, and Enceladus might still be spewing plumes of water into the vacuum of space. The Jupiter-Saturn system, 100 million years from now, will still contain a diverse world, like a mini solar system. Continuing to ignite our imagination, Uranus and Neptune, the silent giants. Further out in the solar system, Uranus and Neptune will remain in their silent realm 100 million years from now. These ice giants, massive planets with interiors rich in ice and rock components, are so far from the Sun that they are almost unaffected by its changes. The increase in sunlight in 100 million years will be negligible by the time it reaches Uranus and Neptune. Not enough to make a difference from the present. Therefore, Uranus and Neptune are expected to continue orbiting near the edge of the solar system, looking much as they do today. Uranus is famous for its tilted rotation axis, which is knocked over on its side at 98 degrees. This extreme tilt leads to dramatic seasonal changes. Uranus has an orbital period of about 84 years, and because of its tilted axis, it experiences an extreme summer or winter every 42 years when one of its poles faces the Sun. This rotation axis is unlikely to change significantly in 100 million years. Uranus has faint rings and 27 known moons, but major changes are not expected. Perhaps once every few tens of millions to 100 million years, collisions between small moons could form a subtle new ring, or an old ring might disappear. However, the interactions between moons in the Uranian system are not as strong as in the Jupiter or Saturn systems, so dramatic events would be rare. As a result, Uranus will remain a quiet, aquamarine planet 100 million years from now. Its atmosphere contains methane, which gives it its bluish-green hue, and this composition should not change. Observations would reveal gentle clouds at best, a calm appearance, without prominent storms like the Great Red Spot. However, since it is slowly losing internal heat, its meteorological activity might be even weaker than it is today. Uranus is sometimes called the most boring planet in the solar system due to its lack of weather changes. And in 100 million years, its atmosphere might be even quieter. Neptune, too, will continue to be a planet of deep blue. Similar to its present state, Neptune has an orbital period of about 165 years and is the most distant planet in the solar system. Its atmosphere has high-speed winds, some exceeding the speed of sound at over 1,500 kilometers per hour, and dark, spot-like storms are sometimes observed. These storms are temporary, lasting from a few years to a dozen or so. Over the course of 100 million years, countless storms will have formed and dissipated. However, the overall appearance of Neptune will be stable, and from a distance, it will always look like a beautiful indigo disk. Since the light and heat from the sun are very weak, Neptune's weather depends on its internal heat source. Neptune still radiates more heat into space than it receives from the sun. Due to an unknown internal heat source, this internal heat will also decrease over time, but not significantly in 100 million years. Therefore, Neptune's wind speeds and storm frequency will likely be much the same as they are today. As always, dark storms called dark spots will occasionally appear and then disappear after a while, showing its whimsical face. Neptune has a largest moon, Triton. Triton has a retrograde, orbits in the opposite direction of Neptune's rotation, so it is fated to eventually fall into Neptune. However, the time scale for this is said to be billions of years or more. So, its orbital radius will hardly change in 100 million years. Triton is an active celestial body, where cryovolcanism, eruptions of ice, is still observed today. It has a slight internal heat source that causes nitrogen ice to erupt. It's uncertain whether Triton will maintain this activity in 100 million years, but it will at least still exist as an icy moon. On Triton's surface, nitrogen ice forms and disappears at the poles with the seasons, and this process is expected to continue. Since Triton's orbit will not change dramatically in 100 million years, it will likely exist in much the same configuration with Neptune's faint rings and other small moons. In the outer solar system, the trans-Neptunian objects like Pluto and Eris, in the region of so-called dwarf planet candidates, will continue their quiet orbits. In 100 million years, these bodies will also exist in much the same way, with only slight changes to their orbits. For example, Pluto has an orbital period of 248 years. So in 100 million years, it will have orbited the Sun about 400,000 times. During that time, the ice on Pluto's surface will have repeatedly sublimated and refrosted with the seasonal changes, slowly altering its topography. Pluto's thin atmosphere will also have frozen and reappeared many times over 100 million years. However, these are microscopic changes, quiet processes, from the perspective of the entire solar system. In short, Uranus, Neptune, and the outer solar system objects will exist in much the same state as they do today, 100 million years from now. Being far from the Sun, they will not experience dramatic environmental changes, and a quiet, cold world will continue to spread out. If we could visit the solar system in 100 million years, after being astounded by the dramatic transformations of the inner planets like Earth and Mars, we might feel a sense of relief at the reassuring constancy of the outer planets. In the darkness of space, Uranus and Neptune will continue their slow orbits, bathed in faint sunlight. Perhaps there, a vestige of a time when the solar system was still peaceful, will quietly remain. Small bodies and cosmic dynamics. The solar system contains countless small bodies, in addition to planets, asteroids, comets, the remnants of planetesimals. They are relics of the solar system's formation and, at the same time, potential threats to Earth. Over a span of 100 million years, the orbits and numbers of these small bodies will also gradually change. Here, let's explore the fate of these small bodies and the impact they could have on Earth. First, the asteroid belt. The asteroid belt, which spreads between Mars and Jupiter, contains hundreds of thousands of small bodies made of rock and metal. Even today, asteroids occasionally collide by chance, shattering and reducing their numbers or creating new fragments. Over the course of 100 million years, such collisions between asteroids will cause considerable reorganization. A larger asteroid might shatter in a collision, becoming a swarm of smaller ones. Or conversely, fragments from a collision could merge to form a slightly larger body. However, in general, shattering is more common, so the total mass of the asteroid belt is expected to gradually decrease. The orbits of the asteroids in the belt are primarily influenced by Jupiter's gravity. Asteroids that fall into a resonance with Jupiter's orbit can have their orbits perturbed and be flung into the inner solar system. The gaps in the asteroid belt, known as the Kirkwood gaps regions, where asteroids have been ejected by orbital resonance, might be even wider in 100 million years. In other words, over a long period, Jupiter will continue to fling bodies from the asteroid belt inward or outward. For this reason, some asteroids will become near-Earth objects and come close to Earth's orbit. Over 100 million years, it's possible that some asteroids currently stable between Mars and Jupiter will have shifted into dangerous orbits that cross Earth's path. The frequency of meteorite impacts that threaten Earth must also be considered on a 100 million year scale. Fortunately, small meteorites, a few tens of meters in size, frequently fall to Earth, but the damage is localized. On the other hand, an impact from a body several kilometers in size would cause a global catastrophe, and a 10-kilometer class impact would bring about a mass extinction level of destruction. Looking at the past record, it is estimated that an asteroid or comet of about 5 to 10 kilometers in size collides with Earth on average once every 100 million years. In fact, it is fresh in our memory that an asteroid impact at the end of the Cretaceous period, about 66 million years ago, led to the extinction of the dinosaurs. Since then, about 66 million years have passed. Unfortunately, no impact of a similar scale has occurred. However, statistically, there is a sufficient possibility of an equivalent major impact occurring within the next 100 million years. In other words, the geology of 100 million years from now might contain traces of a meteorite impact that could have happened in our future, an iridium anomaly or a crater. Think about it. To the organisms that dominate the ecosystem, 100 million years from now, the existence of modern humans might be a legend from fossils, like the ancient dinosaurs are to us. And in the meantime, at least one celestial impact event, wiping out the previously thriving life, might have occurred. For example, if future geologists were to examine the strata of 100 million years from now, they might discover traces of a mass extinction comparable to the KPG boundary of 66 million years ago. The geological layer that marks the mass extinction of the dinosaurs. That layer might be enriched with elements of cosmic origin, like iridium, and countless species would suddenly disappear from the fossil record. If such an anomaly were recorded in the strata 100 million years from now, it would be evidence of a major impact that occurred during this future period. Earth is constantly exposed to the threat of such cosmic collisions. The presence of Jupiter is thought to reduce that threat to some extent. Jupiter is the most massive planet in the solar system, and its powerful gravity often captures comets and asteroids heading toward the inner solar system. In fact, Jupiter has acted as a cleaner, such as in 1994, when it famously swallowed the fragments of comet Shoemaker-Levy 9. However, at the same time, Jupiter's gravity also disturbs the asteroid belt, becoming a cause for sending asteroids toward Earth. So its role is complex. Looking back 100 million years from now, it's an interesting question whether Jupiter will be evaluated as having prevented many more mass extinctions on Earth, or as having threatened Earth with asteroids thrown into strange orbits. Now, besides asteroids, we must not forget the existence of comets. Comets are small bodies made of ice and dust that orbit the solar system in long, elliptical or parabolic orbits. Many comets originate from the Oort cloud, a region at the far reaches of the solar system, tens of thousands of astronomical units away. The comets in the Oort cloud are usually far from the Sun and frozen. But if they are dislodged into the inner solar system for some reason, they appear with long tails. This some reason is often the close approach of a nearby star or the influence of the galactic tide. The solar system is orbiting the center of the galaxy, and along the way, it sometimes passes relatively close to other stars. Observational data predicts that in the next 15 million years, about 26 stars will pass within 1 parsec, or about 3.3 light-years, of the Sun. Furthermore, there will be several near misses within 0.5 parsecs, or about 1.6 light-years. A prime example is the star Gliese 710, which is calculated to approach to about 0.2 light-years in about 1.3 million years. When such a stellar approach occurs, the countless icy bodies sleeping in the Oort cloud will have their orbits disturbed and be sent into the inner solar system. This is what's known as a comet shower. As a result, at certain times, numerous comets will fly through the inner solar system, and the probability of them falling on Earth increases. The hypothesis of a roughly 26 million year periodicity in Earth's mass extinctions, known as the Nemesis hypothesis, or the periodic extinction theory, suggests that comet showers occur when the solar system periodically passes through the galactic plane or during close stellar encounters. This theory is controversial, but the possibility of comet showers occurring as the solar system journeys through the galaxy cannot be denied. By 100 million years from now, such comet showers might have occurred multiple times. If there is a comet shower roughly every 30 million years, that would be about 3 times in 100 million years. Some of those comets could have collided with Earth, affecting the environment. For example, at a certain time, multiple medium-sized meteorite impacts or climate changes could have occurred simultaneously, leaving an imprint on biodiversity. We should also consider interstellar objects that fly in from outside the solar system, bodies that do not belong to any star system, and drift between the stars. In recent years, objects like Oumuamua and comet Borisov, believed to be of extrasolar origin, have been observed and become hot topics. The frequency at which such interstellar objects pass through the solar system is unknown, but over 100 million years, a considerable number might have visited. Most would just skim past the sun's gravity and exit. But there is a non-zero possibility that a rare one could be captured by Jupiter or Saturn and become a new moon. In fact, Neptune's Triton is thought to be a captured trans-Neptunian object, and some of Jupiter's irregular moons might be of captured comet origin. In the future, events such as an interstellar object colliding with a planet or getting lost in the inner solar system might be recorded. Finally, let's touch on the long-term stability of planetary orbits. As mentioned earlier, the influence of Jupiter's gravity makes the planetary orbits of the solar system chaotic in the long term, meaning small differences can amplify greatly over time. However, simulations show that on timescales of tens to hundreds of millions of years, the planetary orbits are kept mostly stable. In fact, high-precision calculations show no noticeable changes in Earth's orbital semi-major axis or eccentricity, a measure of how much an orbit deviates from a perfect circle, for at least about 100 million years. In other words, 100 million years from now, Earth and the other planets will maintain roughly the same orbits as they do today. Therefore, the celestial impact risks discussed earlier are primarily from small bodies like asteroids and comets. And events, like planets colliding with each other, can be considered not to occur on a 100 million year timescale. Some simulations suggest a less than 1% chance of Mercury's orbit becoming unstable and colliding with Earth billions of years from now. But that is a very low probability event in the distant future. As you can see, on a 100 million year scale, the orbital evolution and collisions of small bodies are important topics in the dynamics of the solar system. Events that could have a major impact on Earth include the fall of a giant meteorite, comet showers, and the subtle gravitational manipulations by Jupiter. Perhaps the future environment and evolution of life on Earth will be directed by these messengers from space. The day may come when our descendants discover their traces by turning the pages of Earth's geology 100 million years from now. Relationship with the galactic environment. The solar system is not an isolated island in the cosmos. It is a traveler within a large island universe called the Milky Way galaxy. Our Sun orbits the galactic center approximately every 230 million years. In other words, the solar system is constantly moving through galactic space at a tremendous speed, and its environment also changes over time. Where will the solar system be in the galaxy 100 million years from now? And what kind of impact will the changing galactic environment have on the solar system? Currently, the solar system is located within a small spiral arm called the Orion Arm, or more precisely, the Orion Cygnus Arm. The Milky Way has several spiral arms, which are regions with a high density of stars and regions with a lower density. The solar system is thought to have passed through spiral arms many times in the past. During these passages, the surrounding stellar environment changes significantly. For example, spiral arms contain many new stars. So supernova explosions occur frequently. If a supernova occurs nearby, it can destroy Earth's ozone layer and shower the planet with harmful radiation. In fact, traces of supernova effects on Earth's history, occurring at intervals of a few million years, are being debated. One estimate suggests that a supernova close enough to seriously affect Earth, within 50 light-years, occurs on average once every few 100 million years. This means that about 20 such supernovae might occur in 2 billion years. So, about 10 in 1 billion years. It's possible that by 100 million years from now, 1 or 2 supernovae that could damage the biosphere will have occurred near the solar system. For example, some research suggests that a supernova within 50 light-years could halve the ozone layer for several years, affecting life on the surface. Over a long period of 100 million years, the possibility of such an event happening by chance cannot be ignored. Over the next 100 million years, the solar system is estimated to rotate about 150 degrees around the galactic center. The motion within the galaxy is not a simple orbit, but also involves an oscillating motion up and down with respect to the galactic plane. The solar system is thought to oscillate vertically through the galactic plane, the central plane of the galaxy's disk, with a period of about 30 million years. When passing through this galactic plane, the density of interstellar matter may increase, or it may be affected by the dark matter concentrated in the plane. Some hypotheses link the period of the solar system's passage through the galactic plane with the periodicity of mass extinctions on Earth. The scenario is that near the galactic plane, there are many dense interstellar clouds, like molecular clouds, and when the solar system plows into them, the comets in the Oort cloud are disturbed, increasing comet impacts on Earth. The Oort cloud is a collection of icy bodies thought to be the home of countless comets, surrounding the solar system in a sphere at its farthest reaches. Alternatively, another theory proposes that cosmic rays, high-energy particles from space, increase in the galactic plane, affecting Earth's climate and modulating ice age cycles. In fact, analysis of Earth's climate change data has reported a pattern of cooling with a period of about 30 million years. And some claim this is because increased cosmic rays during passage through the galactic plane increase cloud cover and cool the climate. This theory has its critics and is not confirmed, but it is an interesting hypothesis. Looking closely at the solar system's galactic position 100 million years from now, its relationship with the spiral arms is a key point. The spiral arms of the Milky Way are thought to rotate at a constant pattern speed, and the solar system moves through them. One theory estimates that the solar system crosses a major spiral arm of the galaxy about once every 135 million years. If this is correct, the solar system in 100 million years might be in the middle of passing through a spiral arm, or just after exiting one. Currently, the solar system is at a considerable distance from any major spiral arm, but in 100 million years, it might be approaching the Perseus arm. A change in position within the galaxy means a change in the environment surrounding the solar system within a spiral arm. The density of interstellar matter is high, and as mentioned earlier, supernovae are also more frequent. Therefore, the intensity of cosmic rays will also increase. Cosmic rays can cause nuclear reactions in the atmosphere, potentially having an indirect effect on climate and life. For example, an increase in cosmic rays changes the production rate of certain atomic nuclei in the atmosphere, such as beryllium-10. Future scientists might be able to read the changes in cosmic ray intensity around 100 million years ago by examining ice cores. And from that data, they could estimate when the solar system crossed a spiral arm. Another important aspect of the changing galactic environment is encounters with nearby stars. I mentioned earlier that 26 stars will pass within 1 parsec in 15 million years. Simple calculation suggests that over 100 million years, that would be about 6.6 times as many. Over 150 stars, passing within 1 parsec. A parsec is a unit of distance in astronomy. 1 parsec is about 3.26 light years, or about 3.09 times 10 to the 13th power kilometers. In reality, the distribution of stars is not uniform, and the rate of close encounters with stars depends on the location within the galaxy. The encounter frequency would be higher within a spiral arm where there are more stars. These stellar encounters not only affect the Oort cloud and send in comets, but can also slightly perturb the orbit of the solar system itself. However, the probability of the solar system being captured by another star or being ejected is extremely low. The Milky Way is vast, and events like stars colliding are almost non-existent. A direct collision and merger between the Sun and another star is rarer than the end of the universe. However, the Milky Way galaxy itself will change in the future. In about 4 billion years, it is expected to collide and merge with the Andromeda galaxy. But 100 million years is still long before that. Still, the arrangement of stars within the galaxy will change little by little, even in 100 million years. And the Orion Arm, to which the solar system belongs, might have changed its shape. Perhaps in 100 million years, the solar system will have left the Orion Arm and entered a more empty region. If so, there would be fewer bright stars nearby, and the number of stars in the night sky might be less than it is today. Conversely, inside a spiral arm, the density of stars in the night sky would have increased. The night sky of 100 million years from now will be completely different from the constellations we know. Stars change their relative positions as they orbit the galactic center. Rigel and Betelgeuse in Orion will have moved, and many stars will have reached the end of their lives and exploded. The North Star will, of course, be a different star, and famous constellations will have broken apart and become unrecognizable. The stars shining in the future night sky will be in a configuration we cannot imagine, drawing new constellations. One more thing to mention in relation to the galactic environment is the galactic tide and encounters with molecular clouds. If the solar system were to plunge into a giant molecular cloud, a high-density gas cloud that is the source of star formation regions, not only would the comet orbits around the solar system be disrupted by the resistance of the interstellar matter, but the increased dust could also block the sun's light, potentially causing Earth to cool. However, the probability of this is very low, and it's almost certain that we won't encounter a large molecular cloud in 100 million years. On the other hand, the galactic tide, the influence of the gravitational field from the entire galaxy, is constantly acting on the comets in the Oort cloud. Some theories suggest that as the solar system periodically changes its distance from the galactic center and its vertical position, this tidal force also fluctuates, leading to periods when comets are more likely to fall in with a certain rhythm. This is related to the periodic extinction hypothesis mentioned earlier. In conclusion, the relationship between the solar system and the galaxy is deeper than we might imagine, and is an important factor in painting a picture of the future 100 million years from now. In short, the solar system in 100 million years will be in the middle of its journey through the galaxy, and will likely have experienced events such as passing through a spiral arm or having a close encounter with a nearby star. This could increase the influence of supernovae and cosmic rays, leaving some kind of mark on Earth's environment and life within the vast environment of the cosmos. The solar system is also a being that is constantly being influenced. 100 million years is less than half of one galactic orbit. But even during that time, the galactic seasons will turn, bringing various cosmic events to the solar system, the fate of humanity and civilization. So far, we have depicted the solar system 100 million years from now, mainly from an astronomical and geological perspective. Now, what about humanity and human civilization in this grand future? Will we humans have survived for 100 million years, or will we have already disappeared from the face of the Earth? Passing the baton to another intelligent being, this is not an easy question to answer. But we can consider several possibilities based on scientific knowledge and extrapolations of current technology. First, from a realistic perspective, the probability of modern humans, Homo sapiens, surviving for 100 million years is extremely low. Biologically speaking, it is rare for a single species to survive for tens of millions of years. The average lifespan of a mammalian species is said to be around a few million years. In fact, looking at the hominin fossil record, it has only been about 300,000 years since we, modern humans, appeared. Our ancestors before that, such as Neanderthals and Homo erectus, also disappeared after a few 100,000 to a million years, and no human species has survived for a 10 million year period. 100 million years is an unimaginably long time. Far beyond that, therefore, even if humanity exists in 100 million years, it is highly likely that it will be descendants who have evolved into a form vastly different from us today. From the perspective of biological evolution, it would not be surprising if a completely new species emerged from the primate lineage and became an intelligent life form over the course of 100 million years, perhaps in the future of Earth. We, humans, will have become an extinct branch of evolution, and crows, octopuses, or a completely unexpected organism will have built an advanced civilization. However, humanity is more than just a biological organism. We have civilization and technology. This is a crucial factor when considering the future of humanity. If humans can control their own existence and prosperity, they may become a long-lived species that transcends the laws of nature. In other words, humanity might be able to overcome its biological limitations through technological evolution. So, on a 100 million year timescale, how far will human technology have advanced? It is nearly impossible to directly predict the technological level of 100 million years from now. But we can suggest a few directions. First, humanity may have expanded its sphere of existence beyond Earth, a future where humans, or their successors, are living on planets and moons within the solar system, or in giant colonies in space. Even today, there are plans for Mars colonization. But in 100 million years, it's possible that not only Mars, but also cities at the bottom of the ocean, on Jupiter's moon, Europa, or domed cities on Saturn's moon, Titan, will have been realized. Furthermore, with a time span of 100 million years, it's possible that humanity will have left the solar system and advanced to other star systems. For example, SF-like plans, such as sending probes or colony ships to nearby star systems like Proxima Centauri, taking tens of thousands to hundreds of thousands of years to colonize them, might have been accomplished within 100 million years. Even if we cannot break the barrier of the speed of light, it's conceivable that through generation ships or exploration by super long-lived artificial intelligence, humanity's footprint will have spread over a considerable area of the galaxy. It's also possible that humans will have reshaped their own bodies and intelligence. Even today, there are developments in AI, artificial intelligence, and brain-machine interfaces. In the distant future, technology might be established to digitize the human mind and upload it to a computer. If that happens, humanity might continue to exist, not as a biological species, but as a digital life form or a mechanized intelligence. In that case, radiation and lifespan would no longer be a concern. It's an SF-like vision of the future, where human intelligence remains as giant servers or robots in space, continuing to travel among the stars. The scenario where, 100 million years from now, human bodies are no longer on Earth, but the consciousness of former humans continues to live on in a computational network built on the Moon or asteroids, cannot be completely ruled out. On a slightly more realistic line, it's possible that through advances in genetic engineering and cellular technology, humans will have changed their own form without biological evolution. A new type of human, with enhanced physical and mental abilities to adapt to the environment, might have emerged. It's also possible that living in the low gravity of Mars or the Moon will have changed their physique, creating branches of humanity that have undergone their own unique evolution. Several such human species might coexist, building societies in various parts of the solar system. With a length of 100 million years, human civilization itself might have experienced great rises and falls many times. After an advanced civilization spreads through space, it might decline for some reason, and civilization might be restored again on Earth or at another base. The geological record of Earth will contain abnormal traces left by human civilization: plastics, concrete, radioactive isotopes. But even these will weather over a long time, and traces of other civilizations might be layered on top. However, there is no guarantee that we humans will survive until such a distant future. From a pessimistic viewpoint, it's also possible that humanity will go extinct somewhere in the near future. Nuclear war, climate change, a devastating pandemic, ecosystem collapse risks that threaten the survival of humanity exist even today. Even if we overcome these, astronomical risks such as asteroid impacts, supervolcano eruptions, and gamma-ray bursts will always be present. 100 million years is a long time, and during that period, mass extinction-level disasters could occur many times. Even the dinosaurs thrived for about 160 million years but eventually perished. It will not be easy for humanity to survive for 100 million years. A future where we fall from the peak of prosperity and then disappear is entirely plausible. If humanity were to disappear at an early stage, what would happen to Earth? The nature of Earth would probably be freed from human hands again, and wildlife would dominate the planet. In the first few thousand to a few million years after humans are gone, the remnants of human civilization would rapidly deteriorate. Skyscrapers would collapse and decay. Roads would crack and be swallowed by forests. After a few tens of millions of years, the traces of human cities and structures would almost completely vanish. The only thing that might remain as a trace in the geological layers would be fragments of plastic and glass buried deep underground, mixed in as a human layer. Even that would be scattered and difficult to identify After 100 million years of weathering, for example, megacities like Tokyo or New York are likely to have disappeared without a trace in 100 million years due to plate subduction or erosion. Concrete and steel would return to the soil. Plastics would continue to decompose, and radioactive waste would decay and become safe. In other words, nature is extremely resilient. If humans are gone, the debris of artificial objects might remain as strange artifacts for a while. But time will solve it all. On the other hand, the ecosystem, after the disappearance of humanity, would embark on a new evolutionary path. Large animals that were suppressed by humans might thrive again in various places. The experiment of evolution would restart from there. And in 100 million years, a completely new group of organisms, different from today's mammals and birds, would have emerged. Animals whose habitats are currently shrinking due to human pressure, such as large carnivores, might have diversified in a world without humans. Just as mammals rose to prominence after the extinction of the dinosaurs, some researchers speculate that after human extinction, crows or octopuses might develop intelligence and take over civilization. With a length of 100 million years, it would not be surprising if such a new intelligent species appeared on Earth. Of course, even if that happens, our descendants will have no way to confirm it. Now, let's assume that humanity is lucky enough to survive and maintain some form of civilization in 100 million years. From what perspective will they look back on history? Probably on a 100 million year scale. The entire history of humanity so far, a few thousand to a few tens of thousands of years, is but a fleeting moment. Our current civilization and prehistoric events are like a dot on a million-year timeline. When future humans look back on the 100 million year journey, the present era will seem like a mere instant in the dawn of time. Perhaps it will be spoken of as the beginning of human civilization. That's how vast 100 million years is. And if humanity can survive even that immense length of time, it would be a miraculous achievement in itself. As a technological prospect, let's also consider the possibility of humans responding to the sun's changes. In 100 million years, the sun's luminosity will have increased, and Earth's environment will begin to change. If humans possess advanced technology, they will likely try to survive by artificially controlling the global environment. For example, geoengineering measures, such as artificially adjusting the composition of the atmosphere or deploying a giant shield in space to act as a sunshade to control solar radiation, are conceivable. A more audacious idea is to move Earth's orbit outward. This has actually been proposed by astronomers by using the gravity of Jupiter and other planets to gradually move Earth outward. It might be possible to keep it within the habitable zone even as the sun gets brighter, specifically by having asteroids make close passes to Earth. We could use a gravitational assist to increase Earth's orbital energy, gradually expanding its orbital radius. This is a very long-term, high-risk plan that seems impossible on a human scale. However, if a super-advanced civilization were to continue this effort over a span of 100 million years, moving Earth a few tens of millions of kilometers farther out might not be just a fantasy. Of course, without going to such lengths to stay on Earth, if humanity has already moved its living sphere into space itself, there would be no need to worry about the sun's changes. If they are living in space colonies or on terraformed other planets, Earth might be preserved as the birthplace of humanity. Let's go back a little and think about the case where humans have disappeared. For life on Earth, after humans are gone, the global environment should continue to recover and transform. In 100 million years, a new, diverse ecosystem would likely have blossomed. As the climate fluctuates and the arrangement of land changes, evolution will continue to produce new species. With major impacts and climate changes, extinctions and radiations will be repeated, and Earth will rebuild its ecosystems many times. If an intelligent being, a successor to humanity, or another intelligence were to investigate the past geology on Earth 100 million years from now, they might discover the dinosaur fossil layer from 200 million years ago, the KPG boundary from 66 million years ago, and then, further down, the layer of influence from modern humans, and just above that human trace layer, they might find the traces of a mysterious extinction event, perhaps what could be called the seventh mass extinction layer, likely of meteorite origin. If that were the case, these unknown intelligent beings would surely scratch their heads. They would think, there are traces that a species called humans once existed and built a civilization in this era, but why did they disappear? The answer might have rained down from space, or it might have been humanity's own doing. We don't know if humans will be on Earth 100 million years from now, but if our descendants in that era could watch this video, they would surely think, so this is how humans from 100 million years ago imagined their future. For us, predicting the future is in the realm of science fiction. But for the people of the future, it is history. Perhaps we have a responsibility to pave the way for the future so that we can be proud when they look back. Philosophical conclusion. We have looked at the solar system 100 million years from now. From various angles, Earth's continents will have reassembled. The sun will be brighter. The planets will have followed their respective fates. Asteroids will be flying about, and the solar system will be traveling through the galaxy. It was a mind-boggling vision of the future. But I would like to conclude with a slightly philosophical perspective. First, what is striking is the shortness of human history. On a 100 million year scale, the history of civilization that humanity has built is nothing more than the blink of an eye. Ancient civilizations were born only a few thousand years ago at most, and humanity itself is a newcomer that appeared in Africa only a few 100,000 years ago. Considering that even the age of dinosaurs lasted for about 160 million years, our few 100,000 years is a microscopic thinness on the geological timescale. Our own lives, from the perspective of cosmic time, are like a flash of lightning. After this journey of 100 million years, we can feel the truth of the words human history is but a moment more deeply, but at the same time, I also feel the miracle of existing in that moment. Why are we, in the long history of this universe, born in this particular era, called now? About 13.8 billion years have passed since the Big Bang, and about 4.6 billion years since the birth of Earth. There have been countless moments in between. Among them, humanity built civilization only very recently, and we are in the midst of it. The fact that we are able to perceive the universe as intelligent life, not 100 million years ago, not 100 million years from now, but in this very instant, called now, is, when you think about it, a mysterious and precious thing. Perhaps if intelligent life can survive for a long time, someone or something in the future will look back at our era and say, This is where it all began. The dawn of an age is special in its own way. We are the first species to study cosmology, predict the future, and begin to venture into space. The responsibility and potential that come with that are immeasurable. Depicting the world of 100 million years from now was, in a sense, a way of re-examining our own reason for existence. How fragile and small the existence of humanity is in this vast expanse of time and space. And yet, that fragile existence is now trying to understand the universe. Isn't this something to be amazed by? From the perspective of cosmic history, the birth of humanity and the development of science is an event that happened in the blink of an eye. In that blink, we are exploring the past, imagining the future, and trying to change the future with our own actions. What Earth will be like in 100 million years depends in large part on the laws of nature. But there are parts that can be changed by human involvement. For example, we might be able to develop technology to prevent the impact of a giant meteorite. Or we might be able to control the climate to mitigate the effects of ice ages or global warming. Furthermore, by expanding beyond Earth, we can disperse the risk of extinction. It is also said that knowing the future teaches us how to live in the present by letting our thoughts wander to a grand vision of the future. The importance of the challenges and choices we face now, in the long run, becomes clear. Finally, why do we exist in this era? And how will we build the future from here? When you imagine a future as far away as 100 million years, your daily worries might seem trivial. But conversely, doesn't it make you feel that how you use your limited time is even more important? Our actions may be small, but if they accumulate, they might affect the future of Earth and humanity. The future is by no means fixed. It is something that can be shaped by our hands. The vision of the future drawn today is one story, woven with scientific knowledge and a little imagination. The real future will probably be full of unexpected events. Nevertheless, as long as humanity continues to keep the flame of intellectual inquiry alive and maintains its curiosity about the universe, we should be ready to face whatever future comes. Knowing the future teaches us how to live in the present. With these words in our hearts, let's continue our exploration of the unknown world, and I hope that one day our descendants will look back at this era and say, with a smile, our ancestors did a great job. Thank you for watching until the end. If you found this video interesting, please subscribe to the channel and give it a thumbs up. Also, this channel, Cosmic Lab, has been able to grow steadily thanks to the support of all of you watching. Thank you so much for your continued support. We have set a challenging goal of reaching 100,000 subscribers by the end of 2025. And we are working hard every day to create videos. If you haven't subscribed yet, we would be happy if you would subscribe and continue to support us. Well then, we'll be waiting for you in the next video.